We good? All right. Good morning, everyone, and to our cardiology grand round sessions. And before I introduce our speaker, just some grand round introduction and housekeeping. So for broadcasting, we are broadcasting live via live stream and YouTube. If you're going to have questions, use microphones to ask them. The recording is always available for viewing, and considering subscribing to the YouTube channel, and so you can get all the notifications. For all our viewers, if you'd like to submit a question, text Debaki to 37607. You can also submit questions via live stream feed. And just a reminder, our next conference is Robotic Vascular Surgery Summit. That will be March 25th and 26th. Heart of a Woman on April 27th, and Cardiovascular Disease Prevention May 4th. So for today, I think so what we're trying to address here is a question that's, I guess it's on everyone's mind. Where does the evolving AI role fit into our healthcare processes? And it's truly an honor to have, I would say, the brightest star in this field, digital health, Dr. Rohan Khera, who I have the pleasure of knowing for last 8 years and learning and knowing more of him. Dr. Khera did his, graduated from medical school in India in 2013, did his residency at University of Iowa, and then spent 4 years at UT Southwestern for his cardiology fellowship and MS, and was recruited to Yale in 2020 as an assistant professor. By the way, his CV is much bigger and stronger than a professor, hopefully in a year or two. He directs the bioinformatic core program at the Center for Outcome Research Evaluation. He has a big lab on artificial intelligence and digital health. Has 2 R01s, multiple industry grants, won all the ACC, American Heart Association, American Society of Clinical Investigation, Young Investigator Awards, 2 startups, and just had got a status of FDA breakthrough for one of his digital tools that we'll hear more. And so I can keep going and going, but more importantly, he's also the youngest associate editor for JAMA, the JAMA on digital health and artificial intelligence. And I would just say that if somebody would ask in 2024, who would I like to be born again? Definitely, I would have no hesitancy saying it would be Rohan. And the reason why I say is that, you know, we all agree that in 2024, data is the biggest asset, but as healthcare enterprise, we're still struggling to find the real playbook. And that's where what I admire the most about Rohan's work, that he has taken the lead and give us an insights on the true applications and how do you get things progressed and adopted at a health system, giving solutions to real world challenges that exist for patients, for providers, as well as the health system. So without further delay, Dr. Khera, please give us your pearls of wisdom, and more importantly, why it's important for health system and how that we should invest in big data, AI, and digital health. So thank you so much.
Can people hear me better? Okay, perfect. Thanks, Khera, for that amazing introduction. I don't know if I deserve all of that, but I think we'll dive right in. So first off, I would say that it's a privilege and an honor to be here. Knowing Khera has been in an amazing career transformative experience for me, but for many other people as well. And I think what's been fun to do together is to think about creative problems to solve. And I hope that what I do today is just to share that even these innovations and areas of innovation are largely driven by how you think about problem solving and how we think about solutions that are directly derived from clinical experiences and what we see are gaps in our care. So these are my disclosures. I think the few that I really want to highlight today are that I will present a few tools today. Quite a few of them are actually publicly accessible, but currently they are research tools, so I would not affect patient care directly. And there are, and most of these tools, though, we're trying to get through the FDA. So eventually, the hope is that they can be used in patient care directly. So anybody who's been around AI in healthcare, this is not a new sort of phenomenon to be really excited about AI. We've had a lot of boom bust cycles where previously people had thought that AI is just transform healthcare. We won't need many of our specialists will be out of jobs, and it'll automate all of our care, and nothing will be left in terms of what we do. But anybody who tried to do actual studies of applications, implementation, outcome assessment, found that there was a true lack of impact. Our care processes actually haven't evolved in the last decade. We still provide the care largely the same way. And this lack of impact, if you sort of introspect and think about, is largely driven by the fact that all of our advances have been largely technology oriented and have been largely oriented by, I have this cool technology I want to apply to a patient population that's easy to access, that's easy to deploy in. Rather than thinking about the problems that you wanted to solve and thinking about technology as a solution that is designed to solve that specific problem. And the work we're trying to do is trying to start from that process. So start with defining the critical challenges, identifying nodal points where interventions would make a difference. Then defining the data sources around that nodal point of interventions. And then finally, developing AI solutions that are primed for implementation. So when our development arc follows this thought process and is guided by implementation, it's much easier to think back on implementation being just the path tracking back. So what I will do today is I'll actually walk through a story in 3 parts. The first part is we want to say how we used artificial intelligence to arm our diagnostic strategies with more power. Second, focusing on how do we personalize care for our patients using evidence at its best possible way. And the third is how do we improve quality of care? What we know works does not get used properly enough. How do we make sure people get the treatments they need? And all of these aspects are affected by AI and our digital health transformation. So first off, how do we optimize disease detection through AI? It's not a fact that I need to relate to this room, but a majority of our patients, especially those with structural heart diseases, are often in our community, going about their lives not knowing that they have any disease. And for many of the diseases, there are actually established class 1 therapies where their life trajectory would be meaningfully altered if they were on treatments. However, what ends up happening is even though if they do interact with the health system, it is from low touch contact points. They will do, low risk testing is done in a majority of people, but the testing that is truly diagnostic is done in a minority of people, such that, a minority of people end up getting diagnosed and treated when they're not symptomatic. And it's pretty common for you to see these statistics, and the numbers vary by disease, but, only 1 in 5 people are diagnosed before the onset of symptoms if they have structural heart disorders. And it's also not surprising that majority of these people who are diagnosed end up being from more affluent, with better socioeconomic status. So a lot of our burden of underdiagnosis is overrepresented among the marginalized and vulnerable communities. So, but that's not where we stop, because we've actually now in our day and age across socioeconomic strata have been actually capturing healthcare data in many forms. Many people in our community actually have access to a smart device, typically a smartphone, and increasingly, lower and lower cost smartwatches as well. And it is an increasingly available thing. We did a study nationally, and about 1/3 of the population actually has access to a wearables or a smartwatch. But then there are also interventions like, people go or health maintenance visits. It's still pretty common to undergo electrocardiogram over the age of 50. Then there are, incidental healthcare contact. You went to the emergency room for an unrelated thing, you were coughing and somebody put a probe on your chest, and that information is typically also still captured and stored in health systems. Unfortunately, we are unable to use these tools, in a meaningful way to specifically identify a lot of these disorders. So most people end up requiring that advanced testing still, even though we've been gathering all this data. So our question was whether we can use these early touch points before patients have advanced testing to really empower the diagnostic process, rather than focusing on the complex data, reporting of a large complex MRIs or CTs, but thinking more on the easier data points. And so I'll just use one example to begin this conversation. It's the use of the ACG. And by no means are we the only people looking at this modality, because the idea is that we increasingly have had access to more and more technology that can gather electrocardiographic data from the heart, We've had the 12-lead ECG, like the one you see here, for about a century now. It's looked like this, like a photo printout, for the last 30 years. But increasingly, yes, you can get a 1-lead ECG directly on a wearable device. So while people have focused on the actual raw signal data that comes out of ECG devices to build the tools that can detect structural heart disorders directly from ECGs, our question was whether this photo I show you on the screen can be somehow used more effectively. Because this is the format that, as a clinician, I have access to. And this is the format that clinicians across the world have access to. Can we use this particular data stream, this photo on the screen, more effectively? So we did that through a series of methodological innovations. And our focus was to build a strategy around creating synthetic ECGs that replicated all the noises and variations that might exist in a real-world setting. Pair that with very carefully curated data on gold standards, typically derived from echocardiograms that are done concurrently. Opportunistically close proximity of testing was used as a strategy to inform which ECGs might be closest to people with advanced structural heart disorders. We also identified those who had undergone MRIs, P/P scans, and all other diagnostic modalities, but tried to pair that information with information from ECGs that were designed to replicate real-world noises. And then we built models that can actually identify the complexities on these ECG. As a clinician and as folks in cardiology, you could see that these are different specific areas of the heart, and you're looking currently at the lead V1, and that has different meaning than looking at lead 2 and AVL. And information is actually captured across the span of the ECG. And we try and gather all these data points, and as you train more and more, you're able to see more and more information from the same ECG. So our goal was to whether we can, if we had a model that used the photo to identify patterns of structural heart diseases, specifically we started with LV systolic dysfunction, we would be able to build a tool that could identify these complex associations with outcomes. And that's what we found. We found that with very high discrimination across layouts of ECG, using just a photo of an ECG, we are able to discriminate which ECG belongs to somebody with LV dysfunction, defined as an EF less than 40%, by using a simple tool that can take photos. And because we developed in a very diverse population, performance across the board, across the age groups, across gender, across racial ethnic groups, was consistent. And the most interesting aspect is this is something that you can access today. Unlike any other AI ECG tool, the AI ECG tool that I show you right now, if you scan that QR code, you lead on our lab webpage, you can actually upload an ECG and find it. And that's not to inform care today, but to show the ability to access such technology easily and for people across the globe. And then because we were using ECG images, we didn't have to restrict to a single health system. We could really think broadly. We could think about which partner wants to validate their data, and we went really far. We actually have a clinic here in Houston who just took our model and deployed it in some of their clinic patients. There were people in Missouri. There was a small community hospital, also took a couple hundred patients with a paired EF data and validated our model. Cedars-Sinai did it at scale. So we were able to go across the board. We even sent our tool to Brazil. And in a prospective study where people had undergone protocolized testing, not opportunistic testing, but protocolized ECG echoes done at the same time, we were able to find it. And the images we get look like the images on the left. So these are not like these pristine gold standard images. I want to show the images we were shown for access look like that, with performance still maintained across the board. So really showing the potential of something that's built to scale. And then I think some of the opportunistic stuff that we were excited to see is that when you build a tool that picks up subtle patterns on advanced data streams, you actually are identifying more things than we can comprehend. And some of this recent work, we found that these tools that were designed to be diagnostic, if they were false positive, that means that people didn't have low EF and you got the positive test, those people were fourfold more likely to develop low EF in the next few years. And we've actually gone back and found mechanistic explanation that this is a subtle marker of abnormal global longitudinal strain, suggesting that you are now picking up really advanced imaging markers on simple photos of ECGs. And then I think, while I will not go into the process of describing each model specifically, we've actually used this strategy enhanced with some of our more advanced modeling tools to identify tools that this photo can now be used to detect LV systolic dysfunction, ATTR cardiac amyloid, hypertrophic cardiomyopathy, and aortic stenosis. So if I had to ask that question again, can we use, sorry, that's stuck for a second. Yeah, and I have to say that this ATTR amyloid tool, we were fortunate to actually have the resources from Yale to take it to the FDA, and we got this image-based diagnostic tool for ATTR cardiac amyloid was granted the FDA breakthrough device designation. So if I had to ask the question, can we enhance the value of what clinicians have access to, this photo? The answer would be yes. I think there is the ability for AI to augment our capacity to use this data stream effectively. And it's not only these cool technological things about detecting structural heart disorders. Innovation can actually empower us in many different ways. We're so used to, in our practice, to getting this automated read, right? You get an ECG in your practice, there's an ECG read on top. You can start triaging care. You know who's likely has STEMI, who has AFib. You can think about when to call a cardiologist. This privilege is not something people across the world have access to. And I think we've had a lot of conversations that this is actually a bigger requirement than an echo-based tool for a low resource setting across the world. So we built a tool that it's a novel generation transformer model that breaks up this image into chunks and bits. We train the model to essentially generate a report directly from photos of ECGs. And this too is a tool you can access today. It actually takes images from you and then can generate a full text report directly from photos of ECG. And we're launching multiple studies validating the idea of empowering STEMI networks in places like India and Brazil, looking at these tools to begin the process of triaging ECGs to cardiologists who might be able to confirm them rapidly and start treatments. But I think the role of AI-based even ECG diagnostic doesn't sort of end with clinical ECGs. Because who is the person who's getting a clinical ECG? They're not representative of the general population. And so we thought about, let's extend it to tools that are actually more accessible. And while you may argue, and I would agree with you, that the picture on the left is a marker of privilege and probably is not a person who's not able to get a clinical diagnostic test. But the tool on the right actually is not that way. It's something you can pass around. You can actually put it in any community place that you feel has the highest risk population and actually get 1 lead ECGs, up to 6 leads of ECG directly on the spot. So I think there is 30-second acquisitions of 1 lead ECGs at wherever the person lives is a very powerful strategy. But all we can do right now is pick up AFib. And what's the value of picking up AFib in 30 seconds? All of us would realize that given the nature of rhythm disorders, that's actually not very useful. But that's what these tools have been marketed for largely. But the issue has also been, how do we use these tools effectively for anything more substantive? These are really noisy devices. They don't capture clinical grade ECGs where the electrode and their effects have been perfected over generations essentially, and just get these noisy images. And not only that, we don't actually have very large repositories of 1 lead ECGs derived from these devices and clinical toolkits from echocardiographic reports or CT scans or MRIs. So all these data actually don't exist. And then when you're going to deploy them, you're not going to be able to deploy this in a high prevalence setting. Diseases are going to be rare, so screening is hard. And then there is no integration. There's no way to actually bring these sort of tools into our system and learn how do we deploy tools even in this setting. So we start to solve each of these problems slowly. And I don't think we've solved all of them yet, but we're working on them slowly. So the first thing we wanted to solve was, can we use our clinical ECGs that we're already getting, that we have large repositories of, paired with a lot of imaging data, but somehow make them so that they resemble the ECGs that come from wearable devices. So for that, we took lead 1 data from ECGs. We actually noised them. We took a lot of random noises that resemble tremors, muscle twitching, artifacts, electrode contact movements. All of them actually have frequency bands. And we randomly noised ECGs with these data points. And even stuff that electrical mains affects at a different frequency. And we created these augmented ECGs. And we then trained the model to actually be able to pick up LV dysfunction from these noise ECG. And we tested in another ECG set that actually been noised with noises coming from wearable devices. So from a live core, we extracted noises and actually noised them and did it at a multiple, various levels of signals to noise ratio. With the rightmost aspect is where the noise is highest, where the noise is 2x the signal. And on the leftmost is the clean ECG. When the ECG is clean, a noise adapted model is not needed. I mean, if you have a clinical grade ECG, you don't need to do this fancy stuff. But as the signal becomes noisy, the numbers I'm showing are discrimination. It goes down to about 60% in a noisy ECG, to the point that it's unusable in clinical settings. But if you had the noise adapted model, if you thought about the application, you would be able to retain the performance across the board. And then the idea is like, yeah, LV dysfunction is fairly prevalent, so it's still 3% of the population has asymptomatic LV dysfunction. How do you go to other things? How you do HCM, amyloid, and other things that are very less prevalent? Because whatever you do, you're going to have a lot of false positives. So our thought was maybe we don't need a tool that does diagnostic grade stuff for each thing, especially in this setting. You need something that just gets people to the echo lab, that just gets people from where they are to where they need to be. So we built this tool which specifically takes these noising strategy that I just showed you, but doesn't try to detect LV dysfunction, but a composite of LV, some sort of malignant LVH, some form of severe left-sided valvular heart disease combined with LV dysfunction. And this common tool together actually is able to predict identify LV systolic dysfunction with a very high performance as well, just on a one-lead ECG. And again, the performance characteristics are good enough that you would only get 1 in 2 false positives, which makes that if you were doing for a condition that's prevalent at about 8%, instead of doing 100 tests, you'll be doing 16. So, and I think it changes the game on how we can deploy these strategies at scale. And more importantly, but how would you end up using it? Yeah, you built a tool. Yeah, you have cool models that detect LV dysfunction and other disorders on one-lead ECGs. But how do you get the last mile? So to do that, we actually built our own app, and it's available on the iOS App Store called Cards Plus, and actually takes Apple Watch ECGs. We're actually launching one in Android store soon, with the goal that we can take any wearable device on market except Samsung. They're problematic right now. But like Fitbit, Apple, AliveCore, we can actually run them through the pipeline, and actually that dashboard, that hazy dashboard on the right, actually is predictive performance on HCM, LV dysfunction, valvular heart diseases. So we're able to gather them on source. We can run a dashboard directly coming from the systems, and it can be, this is all HIPAA compliant end to end and can be integrated directly into EHRs using an API. And then, it doesn't stop again. It doesn't stop there, because you've got more modalities to think about. What about cardiac ultrasound? And especially if you're not gonna, make our echo labs, more crowded with a lot of false positives, you really need to be able to use additional technologies that are stopgaps or are essentially funnel the right people into advanced testing. Moreover, as I mentioned, there's a lot of incidental contact now. For training programs outside cardiology, there's a huge emphasis on learning how to do point-of-care cardiac ultrasound. It is happening in emergency medicine at scale. It's actually a billable procedure, so it's actually recorded very well these days. It's happening in perioperative settings, intensive care units, community-focused programs. If you haven't seen, there are a lot of community-focused programs where people are screening communities, not only in the US, but across the world. Point-of-care ultrasound is actually, here to stay. But the issue that we all run against is, even though people are being trained well, they do a good job of trying to get the right view, and it may not be as good as a well-trained sonographer, and they're able to mostly estimate key measures. For them to refer to advanced testing, they have to suspect advanced disorders. They have to really suspect. And they can't really do specialized measurements themselves. They're not going to be able to do a Doppler effectively. They're not going to be able to diagnose a lot of conditions. So many conditions are likely to get missed even with access to this technology. So we took this use case of aortic stenosis. We said, aortic stenosis is 1%, 5% prevalence in age over 65. 1% is severe aortic stenosis. And there is actually class 1 recommended therapy for folks, and especially a diagnostic cascade for them. But most of them require Dopplers to really know that you're really dealing with severe AS. So could we use this video, just this, and diagnose severe aortic stenosis? And it can help us do screening in settings that currently don't have access to this. So in the study that we published in the European Heart Journal last year, we built a new strategy that first teaches a model to read an ultrasound, cardiac ultrasound, without telling it what it is learning for. So the task was just telling the ultrasound machine to know about the models to know which frame comes after which. And that process trains the model to know that they're looking at the heart. And then with small amounts of label data, with about 10,000, with 10% aortic stenosis in a 10,000 sample, we're able to train really robust models that, in an external site, which is hospitals not part of our Yale New Haven Hospital, we're able to show a performance, discrimination of 95% nearly. And it's actually pretty remarkable. It's actually, the plot on the bottom is actually the model prediction for people with no AS, with non-severe AS, and severe AS, and the predictions are, grow over time, suggested that we're picking up patterns. Even though we only train on the binary flag of severe AS or not, the prediction is actually for signatures of disease. And we are able to sort of do temporally different cohorts, like we did only 2021 data, still showing remarkable performance. If anything, we're showing great generalizability. And then finally, we went to Cedars-Sinai. So we do a lot of this where we send models over. We don't ask for data. We send models over. Again, very similar performance, completely new population, able to pick up severe aortic stenosis directly from a single parasternal long axis video. And as I mentioned, this is a continuum. While I may binarize things, we get a continuous probability. And so we call this tool DASI, which is the Digital Aortic Stenosis Severity Index. And a part of that is actually where we binarize the example of high probability of AS. But our goal was, is this also a biomarker of something else? Like, are we seeing a new generation of digital native biomarkers? And we found that. So among people who actually didn't have severe aortic stenosis at baseline, so the plot on the left is AS severity at baseline, vertical axis is annualized change in AV Vmax. We found that even among people who didn't have any AS or had sclerosis, people with a high DASI score, which is the red bar, highest bin of DASI score, there was a progressive increase in the rate of progression to clinical AS. And so we have shown this in multiple different ways. And the plot on the right is the continuous sort of model-derived marginal effect, which just shows that there is a somewhat linear relationship with DASI with increased AV Vmax across types of aortic stenosis at baseline. So I would say we have, in a way, and this will be presented, it was presented at ESC, it's going to be simultaneously published at ACC. What we did find is that there seems to be a new way to define who's going to develop AS and who's going to progress from AS faster, which allows us to personalize our testing, which is so monochromatic these days. And then again, we were able to take it to Cedars-Sinai and show that it actually works across the board. This is progression rate across the DASI bins that I showed before, and we found that even in a new hospital, new setting, new patients, same performance. And again, this is also a biomarker not only for progression, but among people with established aortic stenosis, if we track them over time, there was a higher DASI identified people who actually ended up getting valve replacement more. They actually also ended up dying more, which I don't show here. But the goal overall here is that we're truly picking up a prognostic marker for aortic stenosis that is not only picking up development, progression, but also clinical outcomes. So in summary, this work lets us think about building more capacity with point-of-care ultrasound. And I show aortic stenosis, but we've done a series of cardiomyopathy detection with this and digital progression marker for both development and progression of disease. So all in all, I've shown you three things today. I've shown you a clinician-facing app for ECG diagnostics, something that may be eventually a consumer-facing app that can at least take information from wearables, even if they are not done at the consumer level. And then finally, enabling expert-level diagnosis with AI focus without needing people to get advanced testing. So we're trying to plug that hole, the hole specific that I mentioned before, which is the early disease state where people don't have access to advanced testing. And hopefully this improves the diagnostic modalities by making them more accessible and easy to use. So I'm going to shift gears. So now diagnosis people can, of course, follow because all of us are in clinical practice. We all agree. The harder part is like precision care. And I think this is where you got to trust me to lead you through some more conceptual work, which I think is eventually going to help us deliver better care. Is identifying personalization of care pathways that a person should get. All this work is based on our approach to learning from clinical trials using machine learning and AI, and then learning about individualized treatment signatures, which is identifying what does this patient in front of me need in terms of the data that came from randomized clinical trials. Then second, how do I learn, if I had to do that trial in my health system in this day and age, what would that trial show? And the third thing is, can we just make the trials better and faster? And all these things empower us to deliver better, faster care. So the concept behind all of this, the concept behind all of this is that our current approach to trials is appropriately focused on picking up average treatment effects. Like we've all been taught that we identify people and say, okay, you got people with interventions, you got people with control, half of them got a treatment, half of them didn't, and then we just assess outcomes, and you just count numbers. It's easy. But if you have people in trial, even the highest risk people often don't get an outcome, and the low risk people sometimes do get an outcome. And so how do you not everybody is getting the outcome in the treatment arm and the control arm. And so I think the idea here is that there's definitely some patterns of variation, if not heterogeneity in treatment effect, variation that exists within trials on outcomes in the intervention and control arms. So in a series of studies, we dissected this information out. We wanted to learn whether this variation in outcomes in the treatment and control arms was actually a marker of individualized treatment response profiles. So we went with this concept, the concept being that trials are not case control studies. We don't have a case and a control. We have people, there are a continuum of phenotypes. If you looked at the table 1, there will be all those features are things that vary across people. And say there's a patient, index patient 1. I'm just taking one patient randomly. It is very likely that they are similar to one patient on one axis and another patient on another axis. For example, this patient may be 65 years old, have hypertension, be on an ACE inhibitor, and actually have renal disease. And they might have another person who's 65, has hypertension, but does not have renal disease. And the third patient who has renal disease, he's 56 years old. So now you've started to think that there are these partial matches that exist throughout a trial. And there are people who will be very similar on everything. So that person is closest to me and essentially my digital twin. And other people are farther off, so there are very few shared features. So we asked this question, could we turn the entire trial, take the table 1 characteristics in a trial, and turn them into this multidimensional space where each person in a trial is closest to the person who they are resembling on most features. And then use that information to actually learn about individualized treatment effects. So the projection in the middle is actually from one of our papers, where it's a 2-dimensional representation of a 65-dimensional plane. So you've got to kind of believe me when I say that it is. But what you see is it's a randomized clinical trial, so intervention and control are evenly distributed across the plane. It's random. Like there is no pattern to where intervention and control are delivered. We take one patient, we essentially construct a trial for that patient, varying the distances from that patient to every other patient in the trial. And then computing an effect estimate for that patient conditioned on the fact that this is a person in the middle of that universe. So essentially, we do this for another patient, find a different treatment effect. Third patient, again, different treatment effect. And then we run it as many times as there are patients in the trial. So you run, if it's a 10,000 person trial, you have run 10,000 randomized clinical trials, each at the center of the person who is actually, we are considering the index patient for that stuff. And then we learn the signatures of the patterns that are consistently coming across neighborhoods. For if I had features X, Y, and Z, and I'm always in a group, or more frequently in a group, where treatment is more beneficial, then we can pick up a score that can be used to define who is more likely to benefit. So we just did that. So we built 3 sets of tools, all published now and available again on our lab webpage. You can pick who should undergo stress test versus CTA from the null promise trial, which we validated in the external Scott Hart trial. We took Canvas and Canvas R trials, used Canvas to identify who benefits from SGLT2 inhibitors on the MACE outcomes, and again, validated in the Canvas R trial. And third, we took patients in SPRINT, and we identified who benefited from intensive blood pressure lowering. And in the null accord trial, we were able to identify clearly that the SPRINT pattern of treatment responsiveness carries over in the null accord trial as well. Again, all of these tools are available and we're trying to do prospective studies to validate a lot of them. Well, that's interesting because individualized treatment effects it's hard to power a study for individualized treatment effects. You really want a general sense more than what this patient needs, because if PROMISE needed a few thousand people, the trial that needs interaction on top of PROMISE is a few more. So it's a lot harder trial to run. But what if I'm a clinician, I just want to know, like, hey, you ran this SPRINT trial. What does it mean for my patients at Methodist? Like, what does it actually mean? And you ran the ACCORD trial too, and what does it mean for my patient? So we're trying to leverage this. And again, this is where we're more conceptual than reality yet, is that we want to see whether we can learn from one population the trial was ran in and project what the trial looks like when a new trial would have been done in a different population. And the challenge is there's no gold standard on the EHR side, right? In our real-world Methodist side, we don't know what intensive treatment and lowering would have led to yet. So there is no positive control, so to say. So we said, why not take trials that are positive controls to each other? We know sprint trial exists, and this is an opportunistic choice to choose sprint trial versus accord. Data are publicly available. It's trial testing the same intervention, different populations. Again, yeah, there are variations in how the trial was conducted. There are many small variations across the trials. But largely, you can agree this is a positive trial and a negative trial for the same intervention in a largely high-risk population. So we wanted to see whether if you took sprint patients, sprint trial, and made it look like accord participants, would that trial look like accord? Will the result turn into null? And in contrast, if you took accord and made it like sprint participants, would the outcome change? We did this with this new strategy. And again, digital twins is an approach of turning synthetic data that actually have a lot of shared and covariate relationships maintained throughout the architecture. So we took the index RCT in this example, sprint. We take an external cohort in this example cohort, and we split them one time as well. We identify shared covariates. It's important to know what you're trying to map because you have to know shared covariates, so that comes with some clinical expertise in knowing what they are. We defined actually what we did somewhat uniquely is we didn't do it randomly. We had a clinician sit down and do DAGs, which are these direct acyclical graphs, which know what is an exposure, what's an outcome, what are relationships. We actually explicitly hard-coded that this is an exposure, this is an outcome. And it helps us ensure that it's not random noise. We actually maintain the statistical association or epidemiological associations that are supposed to be in the data set. So these are clinician and expert defined. And then we build a conditional generative adversarial network, or CGAN, to generate RCT digital twins. And these twins are then, we take, say we took 30 columns to generate a digital twin. We took 10 of the columns, data columns, derived from a second data set to then generate the digital twin to see that, oh, instead of taking 30 covariates from sprint population, you took 10 from accord, and then you just generate more trials, like sprint. So how would this look? So on the left, you've got a digital twin of an accord trial, which was the null trial that I mentioned, and then we conditioned them on sprint. The plot on the dot on the top is just the hazard ratio. This is a forest plot. And the hazard ratio of 1 is marked with the dotted line. The green on top suggests accord and sprint. And the right side, you have accord conditioned sprint. So it's a sprint trial conditioned with accord patients. Again, I get it's complicated. But when you condition accord with sprint, you were able to replicate the significant effect in 10 different runs of the same thing, all of them significant. When we ran sprint trial with accord participants, we were able to replicate the null treatment effects of the accord trial. This was, this for us is proof of concept for two things. One, yes, you can do conditional digital twins that are conditional on different populations, and yes, you can adapt them to new populations. But it also tells us that what differences we saw in sprint and accord likely arose from differences in populations that they were there. And so, I think, and this technology just doesn't stop at trials. It enables us to simulate the treatment effects to new populations. And again, that's something we still have to prove based on some sort of prospective assessment. So the last bit in this segment is how do we think about this for evidence generation itself? So there's a trial that starts, a trial that ends, takes 5 years to finish, and we're always like, let's wait for the trial to finish. And we do interim analysis. We either assess them for safety and futility in the interim analysis. Sometimes we'll do adaptive. We'll get creative. And what we'll do is we'll just say, okay, let's have 5 people enroll in the treatment arm and 3 in the control arm because we think that's going to work really faster. But there is no difference in who's enrolled. Like every patient is the same. You get in, you get 3 in control, 5 in treatment. But there's no difference between patients. But I think I've kind of convinced you that there are treatment effects that are embedded in the trial that you can start picking up early in the phase. So we wanted to this is a simulation again of how this new paradigm of adaptive clinical trials might work, is that we actually at interim analysis run our phenomapping strategy, which is our approach of picking up heterogeneous treatment effects from trials at the point of interim analysis. We learn the treatment signatures, and then we stochastically or probabilistically enrich the trial. We don't say don't enroll a population. We just say, you know what, this is a high-risk person based on the features, and it's likely that they should be enrolled in the trial. We don't even say go to the intervention arm. They should be enrolled in the trial. And it's not gaming the trial. We do it all the time. We do risk enhancement all the time. We decide, okay, I'm going to enroll my younger patient or my older patient in a trial. We do that all the time. But this time it's guided by some sort of information that was gathered from the data itself. And the only example I'd use here, we've done this in a few trials now, is the IRIS trial. And for folks who don't know, it's a trial that tested pioglitazone against placebo among patients who had a stroke or a TIA and had impaired glucose tolerance. And pioglitazone was used, and what you see on the bottom are actually different stimuli. So the red is the actual trial enrollment at each interim analysis. The green, the teal thing, is actually if we just randomly said, enroll people more. So that random, of course, choice will not change the trial size. But when we said adaptively, learn from the interim analysis, so learn from the interim analysis at this level, and said, okay, enrich the trial starting interim 2. Then again, learn from that, enrich the trial going through interim 3. In the end, we had a 15% smaller trial size. Again, all simulated, because this is a trial that was already completed. But we were able to get 15% lower trial size at the end without any difference in the effect estimate. And this is done across 10 simulations. Again, no difference in effect estimates and the same p-value. And this is accounting for the O'Brien-Fleming estimates of alpha sharing, everything. So the idea here is that we have the ability to generate information with fewer patients, and again, if you were able to generate, you can run this trial faster, you can achieve the same effect estimate, and the other thing is, each of these trials takes about $40,000 to enroll one patient. So even a small change can really change the cost of drugs to market if those costs are actually shared with the population. That's a big if. Okay, I think I'm going to pause for 1 second, and then I'm going to switch gears to the last thing that we all care about. Is like, yes, it's cool to think about developing new technology. It's cool about thinking about precision care strategies. But how do we make our current care processes better? And this we can all get behind, hopefully. And this is building a new generation of quality measures that are fully electronic, fully automated, fully decentralized. And so it'll help us bring the new generation of CB registries that are not tied to a single site, that are not focused on a single population. But we need to do a lot of things well to be able to achieve that goal. We need to have, of course, easier said than done, interoperability across EHR data sources. So what you build here works even across the street here. A clinician should guide what actually matters, because there's a big separation between what quality measures measure and what people think they measure. And so there's a big gap there. And again, I work at a place that was part of developing a lot of the measures, so I take that with humility. And then finally, how do we incorporate information from unstructured sources? Why do we rely on billing records to do stuff that none of us would use for clinical care? And how can we measure care using billing reports? So we have to solve a lot of problems. The first is interoperability. And I think we've actually done a little bit on that front first, because you can't really go across all these EHR vendors, different EHR interfaces. And if you wonder that going from one hospital to the other makes you have to learn new EHR modalities, and the system looks different, you can imagine the back end for the systems is even more different. So if you had to run a data science pipeline on the back end of a Cerner or an Epic, it's not the same. So what we did instead is, we had to think about, we can't get data from all sites. It has to be the algorithm that travels. But if the algorithm is going to go back on a different data structure than when it generated from, it's just useless. It's worthless. So instead, we actually are creating a body of partner organizations that all believe that let's believe in a data standard. And for examples that I showed before, it could be DICOM and ECG images as interoperable formats. But for EHR, OMOP is a very accepted, and now increasingly NIH supports all of us research program. Everything is in the OMOP research format. And then OMOP data set, what it does really is maps a single set of tables, your demographic table and other tables, into a standard vocabulary. It doesn't do anything fancy, it's a standard vocabulary. So whenever you build a tool on top of this common data model, it can be any algorithm or toolkit, it can be AI, it can be quality measure, whatever. They actually can pass through and run on the OMOP instance of the other system, and actually can deploy and feedback information to the clinicians just as much. And this is just not a concept. We actually are part of this, we're part of this large consortium called Odyssey. And what Odyssey has done effectively is actually found partners across the world. And these are partners who have claims data, who have EHR data, who have like committed to mapping all their data to EHRs. And Yale just joined. We've been doing that for the last couple of years as well. But a few partners that come to mind are the national VA. So all VAs in the country now have a common data source that's mapped to OMAP. So does Columbia, which is being the centerpiece of all of this, Hopkins and Stanford. So we took this, we launched this large study called Legend Diabetes that is assessing many things about second-line anti-hyperglycemic agents. So type 2 diabetes, typically due to metformin. We wanted to see whether SGLT2, GLP, DPP4s, sulfonylureas, what's the use pattern? What's the comparative effectiveness? Can we study at scale like this? So we did that, and I use one example for this. So this is a trend between 2018 and 2021 for SGLT2 inhibitors and GLP-1 receptor analogs as second-line agents. So they were initiated as a second-line agent versus the other agents, DPP-4s or sulfonylureas. And initially in 2018, if you had to look at SGLT2 inhibitors, the use varied a lot. It was low in the VA. It was low at Hopkins, not to call out, but like essentially I think the data showed that there was a lower use there. And it actually increased over time to 2021. But what's really cool about this is not the fact that you can compare head-to-head, it's the fact that you can actually start comparing across the world because we have access to folks in the UK, in Germany, and France. And so what's the European median at that time? What was the national claims showing the pattern of use as second-line initiation? So you can start benchmarking the use patterns across both international and national comparators. And then we could do that, again, in the follow-up years to see who's catching up to whom. And we found that all these centers were above the national median by the time 2021 rolled around. And if you look at GLP-1, we found that European use was much lower than the health systems. And again, we can't distinguish this from obesity versus diabetes use at this stage. But there is definitely it is among patients with diabetes. And we found that most of these were in line with what we saw in national patterns. But as soon as we kept going to 2021, the European uptake of GLP-1 receptor analogs was fairly low, while ours has increased rapidly. And it actually, in these centers, continues to be above the median national use case. But we also saw, and these patterns are what we communicated back to the VA, that we're seeing a really low use among the VA populations, even in recent eras. And it was largely because of their formal restriction on using GLP-1 receptor analogs as second-line agents, which actually has since been modified. So there's a big way to benchmark, assess feedback using these common data models and strategies to do it at scale. And I only use this as a distraction a little bit. We are able to do more when you gather data like this. So the plot here is actually comparative effectiveness done in 1.3 million patients, starting one of the two agents with established cardiovascular disease. And we wanted to see on the left, whatever's on the left side of the screen is actually favors the stuff on the vertical axis. Whatever's on the right side of each bar is actually stuff that favors the vertical axis. And what we found is that among GLP-1 receptor and SGLT2 inhibitors, patients who were started on GLP-1 receptor analogs, had a lower rate of MI going forward. We did not actually find, remarkably, a pattern of differences in heart failure hospitalization. And this was before, STEP-HFpEF came around, and some of the other data are coming around, that there is certainly an overemphasis on SGLT2 inhibitors heart failure therapies, and maybe it's largely a broader effect. Similarly, like Novo just announced the kidney disease results for semaglutide, and they are remarkably positive. So many things we assumed were SGLT2 inhibitor effects might be broader effects, and this data could have forecasted some of that work. We also found, we have never shown this before, but DPP4s, are actually inferior to SGLT2 inhibitors, and as well as GLP-1 receptor analogs on 3-point and 4-point MACE outcomes. And we are able to show across the board that sulfonylureas are inferior to all agents, including DPP4s, on cardiovascular effectiveness. So I think this helps us start thinking about our current therapies more effectively as well. And then I think our big push here is using these things to scale up for quality measurement. So the prior traditional experiences, we have no reliable indicators of processes. Historical perspectives guide current care because claims from last year tell us what we're doing today. There is potential to gain because overcoding and undercoding can change drastically what we do. And it's dissociated from quality improvement. You got to figure out your quality improvement strategy separate from what your measures are. So our goal is to make process-focused measures, make them at the point of care, safeguard them against gaming, and align them with the QI incentives and QI initiatives So an example I use is, HFrEF. More than half of the people are not on guideline-directed medical therapy. This is not news to anyone in the room. There's, limited ability to track who's on, who has HFrEF, like who has this disease. And that's why, even though Get With The Guidelines, Heart Failure, and others provide us with very remarkable evidence, there is no national GDMT program yet. So what we did was we took data from clinical notes in heart failure hospitalizations, such as discharge summaries. We actually built a transformer-based NLP model. It doesn't do like HFrEF as a code. It assigns weights to across the text, picks up, when somebody says no heart failure, the no carries weight as being negative. So it learns this meaning of the text instead of just the syntax of the text. And so taking people who we knew had heart failure hospitalizations, and we knew through historical data their EF, we split them up with who had HFrEF, defined as EF less than 40, or not HFrEF. And ICD codes were very, not useful. Only 20% of people actually had HFrEF diagnosed on ICD codes. But when we deployed our NLP algorithm, we're able to classify most of these people as heart failure with reduced EF. And we were able to validate this data in Northwestern, and we were able to show exactly the same performance, suggesting that we're able to now build and these are light models. These are not like the ChatGPT type large models that are hard to deploy. These can be deployed in any electronic health record without very large computational requirements. So our approach is, enable interoperability, make domain-specific language models to enhance the value of electronic health record, and then make sure you can use some sort of federated deployment strategy to ensure privacy and security. Again, a work in progress. Will probably take several years for us to get through many of these. But then I think at the end of that, we'll have a fully automated measurement of care processes. That's dissociated from care. Nobody is doing reporting of quality measures. It's happening under the hood all the time. And then it actually guides pragmatic quality improvement. So you actually tell hospitals at the point that this patient is not being treated adequately. So they can define QI interventions tied to the quality measure and give feedback to the hospitals with the new measures deployed again post-intervention. And I think the idea is that don't penalize hospitals for having bad outcomes. They penalize hospitals for having consistently bad outcomes despite telling them that they have bad outcomes and bad processes. But I think, one of the last things I would say is that all of the stuff that I mentioned today is interesting, but it can't be done in isolation. There are folks in the room or online who spend their careers thinking about implementation studies, behavioral strategies, how do doctors respond to things. And I think those aspects we're just starting to see with AI. We can build the tech, how do you make it people pick up? So we have to extensively validate to build trust. We have to have regulatory standards behind them so people know what they get, what are the performance characteristics of that tool. And then we have to ensure that there is some degree of interpretability so that this particular tool had a false result because I knew the data was corrupted. And that has to be able, be something we can pick up. And we have to know when there is uncertainty. So the models don't say yes or no, but give you some range of we're not certain where this person might fit in the system. And then we have to build tools that work in all our populations and not a selected set. So, and with that goal in mind, we've actually launched this sort of like Lewis Collaborative. It's very ill-defined. It's called Precardia, and I think what we've done is we've actually found willing participants willing to validate models. We send models over back and forth, and all of us validate these tools, run trials together, are part of multiple now grants and stuff that Khera mentioned, are on grants together based on the work we've done here. So I'd encourage if there are willing participants to join this really open validation strategy where models are shared to validate on people's data, or Precardia. So in conclusion, there is an increased availability of digital data sources in our health systems. AI can assist clinicians, but can also augment our capacity. Technology that is meant for data as they are, rather than changing the entire landscape of health system, is more likely to succeed, in my opinion. And innovation, with AI will actually not only just change care, it will lead to new discoveries, as we've seen the new biomarkers emerging from our work. And finally, there has to be caution about what we learn and how we measure the impact of these interventions. All this work would not be possible without the excellent team at the Cardiovascular Data Science Lab at here, who are all younger than me and are bright and energetic and work like it's no one's business. And you can follow our work on carslab.org. Thank you. And I'll take any questions.
All I have to say, this is wow. This is an amazing newer insights that many of us are still grasping to, and I'm sure there's going to be tons of questions. And I'll just start with one. Just for example, on your ECG tool, which we can upload just an ECG picture and get how can we have that network or connection with an EHR for systems that may be interested in saying, okay, we get thousands of EKGs a day, possibly a linkage to your model for
So I
us.
think one of the things that we've tried to do is actually we don't think data belong to us, so we don't take data. So we've tried to develop everything that works on premises at the centers that work. So we can deploy any of these models that I showed with an API that runs locally in our systems. It is secure. Most people can deploy it in a research setting first to see how it's performing, do some light validation. We can even improve the models based on like if the population is showing a consistent trend towards something else. But it's very easily deployable in the backend ECG systems. And if, I'm sure Methodist as a system has been showing their signals, we can plot those signals and images and do that. But even if it's a small clinic somewhere, there can be phone apps that we can actually load into, devices that are owned by the system and do the entire compute within the API platforms that I described before. So it is all possible and again, currently possible for any participant. It just maybe there's some activation energy always in getting some stuff linkages going, but it's not in any way challenging.
That's perfect. So let's open the forum for questions. Dr. Patel.
Rohan, congratulations on seeing all the amazing work you've been doing since fellowship. Question is regarding you, at the end you talked about the implementation, getting through the regulatory aspect of things. So you highlighted some of the diseases that you're looking at, preclinical disease, and there was a lot of structural heart disease. I wonder, what is the next step what does the regulatory guidance require to get to that stage to get acceptance of this technology? And then what do you think is needed to actually get this implemented in clinical use? And specifically, do you think there need to be trials of these technologies?
Yep, I think as usual, Kershaw and I went to fellowship together. We actually started and ended fellowship the same day, and so it's just great to be here and next to folks that I really have worked for a long time and known for a long time. So I think to your question, we have actually tried to do that too because when this came up, so we formed two startups, largely entirely supported by Yale, no investors. Yale gave us funds and resources to actually go to the FDA. And so we took our tools to the FDA. So they are all regulated as software as medical devices. So they're regulated as devices. So any tool, and so so all of these tools have pre-specifications on what data inputs they will take, what would be the indications for use, called IFUs, if the terminology, and then I think they are standardized. After they are used, they are cleared by the FDA. Typically, they've already cleared two AI ECG tools already. So one is from a company called Viz AI, and which does hypertrophic cardiomyopathy detection from signals of ECGs, so raw signal data. And then there's a Mayo Clinic spin-out called Anumana that similarly has a tool for LV systolic dysfunction from signals. So what our understandings from the FDA is that if your tool has performance characteristics that are useful, they can actually accelerate through something called the 510K pathway, which is it's substantially equivalent but uses a different input. So there is a very rapid path. So why I even bring that up, within the next year, there will be probably a series of tools that are available. And I think what FDA requires, we're actually trying to figure out what the FDA does not need clinical trials to approve devices. Clear devices in the 510K pathway. But we are actually running a lot of NIH-funded trials now. And again, I recuse myself from being the enroller or the analyzer. So because, if I have a financial conflict of interest, but other colleagues are running these trials for us. And then in all these trials, we're trying to see just that, how will we integrate. Our thought is because our tools are designed to be are easy to use and practical, that the integration barriers will be lower if it's a clear tool in market.
Questions? Dr. Khan.
Dr. Khera, my name is Safi. I'm a third-year general cardiology fellow. Amazing work. Congratulations. I have two questions for you. People who believe in the principles of evidence-based medicine, they know that trials have average treatment effect, and you apply them to baseline risk, you get the absolute treatment effect of the patient. And I hope that clinicians who believe that have been practicing it using the clinic in their setting, like using pooled cohort education and getting the treatment effect. Your twin RCT system, how it's going to augment this process. Is it more of a proof of a concept or more of an implementation? And the second question, sir, this is for my own personal education. We have seen the proliferation of these machine learning algorithm-based statistics. And I believe the traditional statistics were 99% of the time give you the same effect. If I'm a reviewer, what advice would you give me in what particular scenario ML is performing better compared to the traditional statistics?
Great questions. I think I'll start with the first one, which is what does the twinning strategy achieve? I think we don't do evidence-based medicine. There's a lot of like gray. Again, I wish we did more evidence-based medicine, but we do a lot of like my gestalt is that this person needs this therapy. In the trial, this person must have been the outlier. We just want to provide you some data points that provide some direction. And it is not meant to be deterministic. It is largely meant to be probabilistic in terms of what you might think and change. I think a lot of in our healthcare and medicine has to become more Bayesian in our thinking. We are taught to be Bayesian without telling us that we are Bayesians, and I think it has to turn in that way. So I would say it is not deterministic. It doesn't tell you what to do for the patient, and if we had to do trials of that specific intervention that I showed you. It has to be done that way. The second question around like when is an advanced tool even needed? I think for some of these, it's actually impossible to run a logistic regression. It's just like there's no alternative. But for others, there might be alternatives. And actually, we published a study in JAMA Cardiology. I was like a graduating fellow. And we took the large NCDR data set, a cath PCI, and did post-PCI mortality, essentially. And we found that post-MI, 30-day mortality and in-hospital mortality, there was no difference if you use logistic regression or some of the advanced gradient descent boosting neural networks. There was no difference. So in wherever there is tabular data, it's actually very hard to beat logistic regression done well. It's just sometimes we don't do it well, and the machine learning models still work okay if you don't do stuff well. And I think that's the value that you derive. That if the inputs are not confounded, like you've taken care of the epidemiological associations, you don't have to rescale the variables. You don't have to think about interaction effects as much as you would need to in traditional testing.
Thank you.
Congratulations. That was really beautiful. And I think what you've touched on, number one, is the amount of work that you guys have done is really amazing. But two, what you've touched on is the impact of AI on so many areas in medicine. And people have to basically embrace it in so many ways. And I think for the new generation, this is your future. There's no question about it. And I love its various applications from diagnostics to many things. I was fascinated and I love the area of twinning because we take for granted that after a randomized trial that we have a drug and that drug will work on everybody who has these very simple characteristics. Yesterday I was a lecture psychiatry and telling us that, with many different diseases, drugs may work at times 10, 15, or 50% of the time. And unless you know some of the either genetics or characteristics that are beyond of what we can discuss, you'll be treating, you'll be giving either therapy or, to somebody who is not going to benefit from it. I think this is a new paradigm for us. And, these technologies would be amazing to try to define further within the cohort that we're trying to do, who would benefit from either this drug or this therapy. So I have two questions for you. One is where you apply it sequentially in an ongoing trial. Are we biasing ourselves to a certain cohort? And I see a positive, but I'm pretty sure you thought about what would be a negative from that because you're changing the course in a trial. So that's one. The other is, what is currently the impediment of applying many of the AI technologies that either you or many other people have developed? Meaning, our EKGs are still the same. They have really not evolved in any way. And I can see that whenever we do a diagnostic modality, whatever the diagnostic modality, would be a suggestion as to what could be the clinical scenario, what could be done for the clinician to be more enlightened.
Yeah, of course. I think thanks for all the great words. And I think I would start with the question around clinical trial optimization. I think it's certainly a proof of concept for us. We do it a lot. Again, you imagine this going through the review process with this. People don't like a lot of innovation. Everybody likes a little bit of innovation. Nobody likes too much innovation. So when we submitted our ECG image LVSD, just as a sidebar, it was so hard to get through. Actually, the journal rejected our paper. Circulation rejected our paper. These are people I trained with. And no favors, clearly no favors. And if anything, a disadvantage. But I think we went back and said, no, you're missing the point. And they made us do so much validation. And we're better off because they made us do it. And I think the entire concept is that let people ask questions, and then I think people like us need to be accountable who are developing tools, and then actually build networks so we can validate and show in many settings. And for trials, I think the corollary is that we actually showed that there was no demographic shift, that we're not enrolling fewer women. We're not suggesting. Plus, you can actually take and actually hard encode that I will not enrich based on these populations, because it's all explainable. It's not like a hidden model. You know which inputs you're enriching the population on. So you can say, okay, I am not going to enrich on any demographic characteristic. If anything, I'm going to monitor that the demographic characteristics don't evolve adversely. That was the first thing we did. Second, we would say that, yes, it's likely that the treatment effect changes, is conditioned on the input population. There are two ways to think about it. We already do this in trials, and we don't care, right? We enrich the trials for, the trial range may be enroll everybody from 40 to 85. We enroll a 75-year-old and a 70-year-old, and the majority of the trial lives in that. We have enrolled men and women at a 90 to 10 ratio for decades. And again, we're seeing the downsides of that, but we've been doing a modest optimization is likely still consistent, and if you're looking at average effects. The second is, how hard is it to deploy a tool before you do the treatment? Like, it is use this tool that shows the high benefit and deploy it before the point of treating, because you know that this particular tool definitely works in this patient. So I think both those treatment paradigms can be easily paired with the evidence generation paradigm. Regarding application, I think, as I alluded to, I feel like it's largely around building trust. In healthcare, healthcare moves at the pace of trust, I think, and if we can garner trust for any technology, people see its effects. So I actually again, observationally, when I get a patient in my practice, I actually apply these tools, like, oh, this person got an echo. I'm going to try and see if my model works. It's worked pretty well. And I think I start feeling confident telling other people about it, only because I know it seems to work for my patients. And again, I think as more people see that in practice, more people see this in use and say, you know what, I referred a patient based on this test, and they got diagnosed with something. I think that'll build the strategy to, we picked up all these tools just using that trust mechanism. Evidence plus trust.
Rohan, I'm a heart failure transplant cardiologist. Wonderful talk. So, we use this pretty much on a day-to-day basis for our heart failure patients undergoing evaluation for LVAD or transplant, where you're really evaluating, what is the benefit, what is the risk. And in fact, OPTN in next year is actually wanting to incorporate probability of success with a transplant for an individual patient, which is so difficult to determine, into the model in allocating hearts. And we don't have any randomized controlled trials in transplant, right? So do you foresee a use of registries in these kind of, twinning where, the treatment effect obviously is huge, but yet, you don't know the relative benefit for each patient?
That's a great question. So I think, if I might say, so we published that paper in JAMA. I was part of the review process in that, of one of those articles that came out in the last few months, where it was one of the scores that are developed and is going to be incorporated in the allocation process. And the conversations are all around this. Whether a statistically derived, effect estimate closely resembles the true effect in that patient, and it's hard to know. I would say if the twin technology, if it's based on just structured input, is actually kind of weak. Like, we do show the trial stuff, it kind of works, it shows the effect. What you're going to really do is, we are not restricted by inputs that are like tabular. We don't need AIDS, X-rays, and all this, only those things. We can actually take raw ECG data, raw echocardiographic video, MRI data, baseline testing, all sort of biological testing, all the gene profiling that might have been done. So I think when we start doing twins of population based on very rich phenotype and genotype information, I think then we can certainly start building strategies which say, in this particular phenotype, with high reliability, I can say this person is not a great transplant candidate, or needs to be accelerated through the transplant process because their outcomes will substantially different. So I think we're like early in that process, and it's harder to do with, like, I would say, as I said before, just machine learning applied to tabular data only achieves marginal benefits.
Well, Rohan, this has been a fantastic, fantastic conversation, and definitely not the end, but I would say the start of many new things. And as Dr. Zogby said, for the future, at least for the future generation, this is where we need to invest a lot. But the key thing where I say is, where would be the investment coming in, especially from the health systems? I know we spend a lot on the IT. The question is, would we really need an AI team for discovery, development, and deployment? So ongoing conversations, and that. Look forward to your thoughts. Thank you.
Thank you.